Hi everyone, welcome to Dr. BT's Chemistry Essentials, making A-level chemistry easier to understand.
In this lesson we are going to look at Year 1 Equilibrium and KC, and we're going to cover these specification points. First we'll start by looking at dynamic equilibrium and then looking at Le Chatelier's principle after that. We can show a typical reaction, AB being the reactants going to CD like so. We know that this is a reversible reaction due to this reversible arrow, and all reversible reactions can undergo something called dynamic equilibrium. Now, dynamic equilibrium only occurs, in closed systems. So the system has to be closed. What we mean by a closed system is the fact that no matter can enter or exit. And to understand what dynamic equilibrium is, we need to just appreciate what the arrows are representing. So the arrow here, going from A to B to C to D, is what we call the forward reaction. And this has a rate, so I'm going to use a small lowercase k to designate rate, and this is forward, so KF for forward. So this arrow represents A and B changing into C and D. On the reverse, C and D, the products, can go back to reactants, and this rate is called KB, rate of backwards. So we have rates of forwards and rates of backwards. Now, at dynamic equilibrium in a closed system, KF, the forward rate, equals KB, the backward rate. So what this means on the macroscopic scale is the concentrations of the products A and B stays the same, and the concentrations of the products stay the same. But what we know on the particle level is C and D is going back to A and B is going back to C and D. But because these rates are the same, we can't observe these changes. We could see this graphically through a graph that has time on the x-axis and then concentration on the y-axis. And if we plotted the products in red, you'll notice it's very steep at the beginning, and then it starts to level off until it plateaus out. Now the reactants in blue, at the very beginning, again there's a steep decrease that starts to level off, and then you plateau out. Something to note is the rates here. So obviously lots of reactants at the beginning, so there's the concentration means that there's loads of collisions, and this also therefore means that more products are being formed. So the important bit is these areas here where it plateaus off and plateaus off here. These are basically the area at which they both plateau off, is the start of the equilibrium state. So we know that this point here and this point here is where we are at equilibrium, and that's why there is no change in the concentrations and the concentrations here over time. So that takes us through explaining that a dynamic equilibrium exists in a closed system when the rate of forward reaction is equal to the rate of reverse reaction, and the concentrations of reactants and products do not change.
Next, we're going to look at Chatelier's principle and its application for homogeneous equilibria to deduce the effect of change in temperature, pressure, or concentration on the position of equilibrium.
So Le Chatelier's principle is the idea that when a change is applied to a system in dynamic equilibrium, the system reacts in such a way to oppose the effect of that change. And what we mean by these changes are changes in conditions. And so if we change a condition, the system, the reactants and the products and the amounts of them, are going to change in order to get back to a state of equilibrium. First one we'll look at is the idea of concentration. Imagine we have this reaction at equilibrium. So our reactants hydrogen gas and iodine gas going to hydrogen iodide. Now, if my change is going to be increasing the reactant concentration, and in this case we're going to go with the idea that we increase the amount of H2, then the system wants to basically counteract that change. So it's going to want to decrease the amount, okay, or the concentration of H2. So it does this by changing the position of equilibrium and shifting it to the right hand side. So this being the left hand side, this being the right hand side. If we've got more of H2, the way it's going to decrease it is by shifting this reaction to produce more hydrogen iodide. Thereby, if you increase the amount of hydrogen iodide, you decrease the amount of H2. Now, opposite wise, if we decrease the reactant concentration, again H2, then the system wants to oppose this change, so it's going to want to increase the amount of H2. And so you're going to have a shift of equilibrium to the left hand side. So hydrogen iodide basically decomposes back down into hydrogen and iodine, therefore increasing the amount of hydrogen, producing more hydrogen. So take, for example, this iron 3+ reactant thiocyanate. What would happen if we increased the amount of iron thiocyanate in this system? I want you to just pause the video here and write down your explanation. Okay. What you should have answered is that the position of equilibrium will shift to the left to decrease the amount of iron thiocyanate. Now, another condition that could change is the idea of gas and pressure. So here we have the Haber process, which is 1 mole of nitrogen reacting with 3 moles of hydrogen to form 2 moles of ammonia gas. Now, just like before, if we increase the gas pressure of a system, the system wants to oppose this change, so it's going to try and decrease the pressure. Now, the way this decreases the pressure is by it selects the side of the equation. So it's handy thinking of the equation as 2 parts, the reactants and the products. It's going to choose the side of the equation with the least gas molecules. Now in this case we have 2 moles of gas on this side, and on this side we have 4 moles of gas on this side. So what happens is it shifts the position of equilibrium to the right hand side, so this side here, because this has the fewest moles of gas, so 2 to 4, therefore decreasing the amount of pressure. Now on the other side, if we decrease the gas pressure of the system, then the system wants to increase the pressure, and so the position of equilibrium will shift to the side with more moles of gas. So the way we phrase this is shift position of equilibrium to the left hand side, because as your explanation, there's more moles of gas. So taking this example of hydrogen and iodine forming hydrogen iodide, what would happen if we decrease the pressure? I want you to pause the video and have a go at this. Okay, so if we decrease the pressure, nothing would happen. The reason being here, and vice versa if we were to increase the pressure, is because on the left hand side of our arrow we have 2 moles of gas, and then we also have 2 moles of gas on the right hand side. So there's no selection, there's no shift in equilibrium, because they're comparable. 2 to 2 would mean there's no change in the pressure. One other thing before we go on, always be aware of the state symbols, because when you're counting the moles, you are counting the moles of gas only. So here it was comparable because they're all state symbols gas, but if you're presented with a reaction where the state symbol is solid, liquid or aqueous instead of gas, then don't include this in your evaluation. The next factor is temperature. Now, if you increased the reactants and the products, the system's temperature, then the system wants to react by this to decrease the temperature. Now, to do and to know how to respond to this, you need to know some information about the reaction that you're looking at, okay? Now, next to the reaction scheme, you'll be given a delta H, which we know is enthalpy change, okay, or overall enthalpy change. And for this particular reaction, we know it is minus 197. What that's telling us that going from reactants to products in the forward direction, it's worth minus 197. So we know minus is exo. So we could label above here as the forward direction being exo. And with this, the reverse reaction, products going to reactants, must be the opposite. So this is endo. And so it's minus 197 going forward and the opposite plus 197 going backwards. If we think about it, if we're increasing the temperature and the system wants to decrease the temperature, the way it can do that is by actually absorbing any kinetic energy and changing it into chemical energy. And so this process of taking that thermal kinetic energy and locking it into the bonds, into the chemical energy, is basically what is endo. So to decrease the overall thermal energy, we need to lock it into chemical bonds, so it's going to favour the endothermic reaction. As stated here, favours the endo direction, absorbs thermal energy. And so the position of equilibrium shifts to the right hand side. So products turn into reactants, this is endothermic, absorbs that excess energy, therefore decreasing the temperature. Now the opposite happens if we decrease the temperature. Basically, therefore, we want to increase the overall temperature of the system. And doing so, we're going to take some of the chemical energy locked in the bonds and make that into thermal kinetic energy. And this process is exothermic. So in this case, it favours the exothermic direction. And therefore, the position of equilibrium shifts to the left-hand side. Therefore, this part tells us the reactants are moving to the products. So for the following reaction, if you're told that delta H is plus 131 kilojoules per mole, what would happen if you were to decrease the temperature? Please pause the video and have a think. If you said that decreasing the temperature shifts the equilibrium to the left, then you're right. This is all because of that plus 1.31, showing that this forward direction is endothermic, and so this is exothermic. Now, if we decrease the temperature, what we want the system to do is to increase the temperature. It can increase the temperature by releasing energy, so it's going to prefer the exothermic. So in this case, you have the position of equilibrium shifting to the left hand side, and therefore we have more of the carbon and the water produced. Now the final idea is the introduction of catalysts, and they have no effect on the equilibrium. The reason being is if you take the generic A plus B going to C plus D, catalysts speed up both the forward direction, A to B going to C to D, and the backward direction, C to D going to A to B, at the same rate. So the position of equilibrium stays exactly the same point. So going back to our links here, we have explained Le Chatelier's principle, an application for homogeneous equilibria to deduce the effects of temperature, pressure, concentration on the position of equilibrium. Now, just a note, homogeneous equilibrium means the same state. Also, we've explained that catalyst increases the rate of both the forward and the reverse reactions in equilibrium by the same amount, resulting in an unchanged position of equilibrium. And this phrase is a good one to basically learn. Next up is to describe techniques and procedures used to investigate changes of the position of equilibrium for concentration and temperature. An example of an equilibrium reaction that lends itself to investigation really nicely is cobalt in two different forms. The hexa-aqua cobalt is pink, whereas the cobalt tetrachloride complex is blue. The easiest thing to investigate is the change of concentration. So if we used a chloride source such as hydrochloric acid and increase the amount of chloride by increasing the amount of hydrochloric acid, then we expect the position of equilibrium to shift to the right hand side to use up the excess chloride, and so the solution, if it was a mix of both these cobalt complexes, would be more blue as we shift it towards this side. Vice versa, if we decrease the amount of chloride, then the position of equilibrium would try to increase the amount of chloride and so would shift to the left hand side. Thus the solution will turn more pink because this cobalt complex is pink. In terms of investigating whether or not it's endo or exothermic, if you took a test tube of an complex in equilibrium, then if we were to increase the temperature of that solution by putting it, say, in a beaker of boiling water from a kettle, then depending on what colour it changes into, tells us which side of the reaction it's shifting towards. So in this case, if we increase the temperature and we find that it turns to become a more dark blue colour in the test tube, then we know that increasing the temperature, typically equilibrium would then favour, from the theory beforehand, the endothermic reaction. Now the fact that our test tube has become more blue means it's shifted to the right hand side. So this is telling us that we have the right, going from left to right is endothermic, and vice versa, therefore this must be exothermic, going right to left. To prove this, if we use the conditions of decreasing the temperature by putting a test tube of a solution in ice cold water, then what would happen, we imagine, is a pink complex is formed because this is exothermic. So the reaction is trying to warm the system back up by going the exothermic reaction. Most investigations of equilibrium involve colour change, so that's really key, especially in year 1. In year 2, you can also use titrations to work out the amount of acid and base there is at the end of equilibrium, but we'll be looking at that in the second year video on KC. Examples of other colour change reactions are Fe3 plus thiocyanate ions going to Fe SCN2+, and that's all because the Fe3+ is yellow, whereas the iron thiocyanate is blood red. And you can see other examples of these throughout. Having looked at techniques and procedures, we then need to also think about how the chemical industry compromises equilibria and reaction rate, as well as cost in its operation conditions. To illustrate industry and equilibrium, we're going to look at the Haber process, which uses nitrogen and hydrogen to produce ammonia. It is a exothermic reaction in the forward sense and is a nice illustration of three effects: the increase and requirement for the yield of ammonia, compromise of the rate of reaction, and also the cost of the operation. So the temperature, if we were to increase the temperature, then obviously our rate of reaction would increase as there'd be more collisions between the nitrogen and the hydrogen, and thus produces ammonia. However, the problem is the forward direction is exothermic. So if we were to increase the temperature, we would actually be favouring the endothermic pathway, which is the backwards reaction. Now, the highest yield would be at 200 degrees Celsius due to the fact that this relatively low temperature would produce more of the ammonia because of the lower temperature preferring the exothermic pathway. But the problem with this is that it actually gives a low rate of reaction, because at lower temperatures the collisions between nitrogen and hydrogen are less. So the compromise here is to actually increase the temperature enough so the rate of reaction is high, but not to damage the yield too much. And so the compromise made, okay, is 450 degrees Celsius, because you get a better rate of reaction there and the yield doesn't suffer too much. The next factor is pressure. So in terms of pressure here, we basically have 4 moles of gas on this side versus 2 moles on the gas on this side. So to get more of the ammonia, we would want really high pressure. So a pressure of about 400 atmospheres would be both good for the yield based on this argument presented, and also good for the rate of reaction. But the problem is it's very expensive to industrially have that really high pressure. The equipment costs a lot, so we can't use that. Instead, what the actual industrial usage is 200 atmosphere. This is good for yield, it is good for rate of reaction still, and also is a compromise to allow for cheap manufacturing costs. The final thing in industry is the use of an ion catalyst, and this obviously increases the rate of reaction. It has no effect on the yield, as we previously said. And so if you increase the rate of reaction and you're making more product in a shorter space of time, you also get costs down, because time is money. So the final thing to look at is this idea of Kc, which we delve into in a lot more detail in year 2. Kc is known as the equilibrium constant. Now, it differentiates itself from rate in that the K is a capital K, and this is subscript C, whereas rate is lowercase k. Okay? Kc as an equilibrium constant gives you an idea of the concentration of the products and reactants at equilibrium. So it basically tells us how far left or right the position of equilibrium is. So for example, taking this generic reaction equation where A, B, C, D are your reactants, and these lowercase a, lowercase b, lowercase c and d are the molar ratios, or the stoichiometry. So for example, this could, if this was a 1, it means there's 1 mole of A. If it was a 2, it means there's 2 moles of A. Then we can generate the equation Kc based on this idea here, that Kc is the products, the concentration of all the products, divided by the concentration of all the reactants. And just to remind you, square brackets always means in chemistry, square brackets always is moles per decimeter cubed. So for our reaction above here, Kc is going to look like this. Products are C and D. We're going to put them in square brackets to show that their concentration. Reactants are A and B. And importantly, the stoichiometry, so the A here, whatever the molar ratio is, then your concentration of A is to the power of that. So if there was 1 mole of A here, it would be A, the concentration of A to the power of A. And then whatever B is, whatever C is, whatever D is. And obviously these next to each other basically means multiplication. So taking into account this reaction, the Haber process once again, if we were to have to generate a equation for this, it would be Kc equals NH3, the concentration of ammonia in square brackets. And due to the fact that it's to the molar ratio 2, you would basically put a square here, divided by, so that's products, divided by reactants, N2, and that is just to the power of 1, so we don't need to show that, times H2 to the cube, and that's all down to the fact that there's 3 moles here. In year 1, you'll only ever be expected to do homogeneous Kcs. This makes sense because nitrogen, hydrogen and ammonia in the Haber process are all in the same phase. Okay, so they're all in the gas phase. Heterogeneous Kcs you'll have a look at in year 2, so don't worry, you won't be expected to do any that have different physical states. The units of Kc itself can change depending on the concentrations above and below in the products and the reactants. So for this particular reaction, it would be mole dm cubed because of the square brackets, but we've got a square there for the ammonia. And then on the bottom of the brackets here, we have moles per dm cubed times moles per dm cubed. This can be written out as mole 2 dm minus 6 because of the fact that we've got this here and we're just basically multiplying out what's inside of our bracket. And then on the bottom, all these combined means we have mole 4 dm minus 12. Again, due to the fact that we combine the 1 mole here and the 3 moles here to make mole 4. And we've got dm minus 3 here. And then we've got dm minus 3 here. So collectively, there's 3 lots of those. So that's minus 9. Minus 3 is the minus 12. And then what we do is we basically cancel down. So mole 2 can go off the top line, leaving mole 2 on the bottom line. dm minus 6 can cancel out of there, leaving minus 6. So our new equation is going to be mole 1 over mole 2 dm minus 6. And this basically can rewrite itself as mole minus 2 dm 6, because basically what we've done here is inverted this equation, bring these to the top so their signage changes, minus 6 to 6, etc. And so you could really think of this as basically reading exactly the same as putting a 1 on the bottom. But we would then say the units of this Kc are whatever the value of Kc is, mole minus 2 dm 6 on our answer line. So imagine we're given this as a question to work out Kc of this reaction here, and given these particular values here. So we know that at equilibrium the concentration of nitrogen, hydrogen and ammonia are given here. If we were to come up with a value for Kc and its units, we would first of all construct our equation. So looking at the actual equation, we come up with this. Then all you do is substitute in the values of the concentrations at equilibrium. So the first one coming from the ammonia, nitrogen 0.142 times by the hydrogen, which is 1.84, and then cubed. What you then do is you put that into your calculator, you get 2.09. And then finally, using the same method we used earlier, you would come up with the units for this as being mole minus 2 dm6. And so you would basically put this in here. Finally, a word on what Kc actually means in terms of what the numbers tell you in terms of the position of equilibrium. So as Kc is a product concentration over reactants, it is basically the same as looking at the ratio of the product's concentration to the reactant concentration. So we're thinking about a ratio here. If Kc is 1, then it means there are exactly the same reactants and products at concentration. So Kc of 1 equals a ratio of P for products, reactants as being 1 to 1. If the amount of products to reactants is greater, then Kc is going to be greater than 1. Just to use these values here, if we thought about it, Kc equals ratio of products over reactants. So if we make 10 from the products divided by 1 of the reactants, so Kc would come out as 10 over 1 is 10, so high. So this is telling us the proportion of products is much greater. Now if we think about this in terms of a reaction, then what you could think of is A plus B going to C plus D. Well, Kc of 10 is telling us that there's more products, so the position of equilibrium has shifted to the right hand side, as stated here. So whatever you're looking at, you know more C and D, the higher yield of C and D, because Kc is greater than 1. Finally, on the reverse of that, basically if Kc is less than 1, then you know that the ratio is more favourable towards the reactants. To again use some simple numbers, imagine the amount of products we got is 1 to a ratio of 10 of reactants. So Kc here is going to be 1 on the top line because it's products on the top over 10 on the bottom. So this is the same as saying 0.1. So Kc is less than 1. And in this case, in our reaction A plus B going to C plus D, then the position of equilibrium has shifted to the left-hand side because we've got more reactants than we have products. So that concludes all of these specification points from the expressions of the equilibrium constant and the idea of estimating the position of equilibrium from the magnitude of Kc.